Welcome to Calculus. Today we are going to explore the foundations of calculus from zero. Why do we learn calculus? Why do we need it? And most importantly, how does calculus actually work? Calculus is fundamentally built on two core ideas: change and accumulation. Differentiation mainly studies change and the rate of change using tangent slopes. Integration mainly studies accumulation. It allows us to add infinitely many tiny pieces together to compute a total area. Together, they form a perfect duality. Differentiation equals rate of change, and integration equals accumulation. First, consider a car. As position changes with time, calculus calculates speed, and how speed changes gives acceleration. Second, water filling a tank. Calculus describes how quickly the height rises and how much total liquid accumulates. Third, in business, profit graphs show where revenue grows fastest and precisely where profit reaches its absolute maximum. We now enter part 1. Differentiation. If you are new here, please subscribe to the channel, because we are going to build calculus from the ground up. Consider curve y equals f, x. Pick point P and nearby point Q. The slope between 2 points gives the average rate of change. Now let h approach 0. As Q approaches P, the secant line smoothly becomes the tangent line, defining the instantaneous derivative. When the graph rises, the derivative is positive. When the tangent becomes horizontal at turning points, the derivative is 0. When the graph falls, the derivative is negative. Local maxima and minima always occur where f prime of x equals 0. Suppose you sit down to eat a big plate of biryani. At first, you are very hungry, so your eating rate is high. After some time, you become full and your eating speed decreases. If y represents the total food eaten, then dy over dt tells us how quickly that amount changes at any single moment. Start with the fundamental limit definition. Substitute x plus h into the function x squared. Expand the binomial in the numerator. Cancel the x squared terms. Divide each remaining term by h. Taking h to 0 leaves 2x. Thus, the derivative of x squared is definitively 2x. For x cubed, power rule brings down 3 to get 3x squared. For 5x squared, we get 10x. For a linear function 7x plus 4, the derivative is its constant slope 7. For polynomials, differentiate term by term. Power rule. Multiply by the power and decrease the exponent by 1. Constant rule. Constants do not change, so their derivative is 0. Constant multiple rule. Pull constants outside. Sum rule. Differentiate each function individually. Product rule. Derivative of first times second plus first times derivative of second. Quotient rule. Bottom d top minus top d bottom, over bottom squared. When a function is nested inside another, the chain rule states: multiply the outer derivative by the inner derivative. For quantity 3x plus 1 squared, the outer derivative is 2 times 3x plus 1, and the inner derivative is 3, yielding 6 into 3x plus 1. Differentiation powers motion equations in physics, maximizes container volumes, optimizes corporate profit, and models population growth. Can we reverse differentiation? If the derivative is 2x, what function did we start with? Integration provides the exact answer. Differentiating x squared plus 1, plus 5, or minus 100 all produce 2x, because the derivative destroys constants. Since we cannot know the original constant from the derivative alone, integration always adds plus c. To find the area under a curve, we approximate by slicing the region into vertical rectangles. As we increase to 20 and then 100 rectangles, the approximation gets closer and closer. In the limit of infinitely thin slices, Riemann sums yield the exact definite integral area. The power rule for integration adds 1 to the exponent and divides by the new power. For composite integrals, U substitution simplifies the variable to evaluate the antiderivative cleanly. A definite integral computes a specific numerical area between bounds A and B. Here, integrating x squared from 0 to 2 gives exactly 8/3. To find the area trapped between curves y equals 2x and y equals x squared, integrate top minus bottom from 0 to 2, yielding 4/3. By setting up the circle equation and integrating the upper semicircle across minus r to r, calculus rigorously proves that circle area is pi r squared. An ellipse is simply a circle stretched horizontally by A and vertically by B. Scaling the area integral transforms pi r squared directly into pi a b. Differentiation measures instantaneous change. Integration measures accumulation. These two operations form an eternal, unified mathematical loop. The fundamental theorem proves that differentiating an accumulated integral restores the original function. Calculus is not simply a collection of formulas, it is the universal language of change and accumulation. In the next lesson, we will dive deeper into advanced problem solving step by step. If this video helped you understand calculus, don't forget to like, subscribe, and I will see you in the next lesson.